Hello everyone and welcome back. My name is Mr. Cobalt, and in this video we're going to be going over a problem where you're given initially some amounts of reactants and then you're told how much of a particular product you have at equilibrium, and then what you do is you add or remove a certain amount of a certain substance and you see what the changes are when it reestablishes equilibrium. So let's get into this. Okay, so here's the problem. A mixture of 0.75 moles of N2 and 1.20 moles of H2 are placed in a 3.0 liter container with an iron catalyst and heated under pressure to 750 Kelvin. And so we got two questions to answer. The first question A, when the reaction reaches equilibrium, H2 concentration is 0.10 molar. What is the value of N2 and NH3 concentration at equilibrium? And then the second question is, if a 0.30 mole or amount or moles of ammonia is removed through condensation and no other gases are added, what are the new concentrations of N2, H2, and NH3 when the reaction reestablishes equilibrium? And we have our balanced equation right here. And so let's go ahead and start to do letter A. So the first part, they want to know what the equilibrium concentrations are of the nitrogen and the ammonia at equilibrium. And so they gave us the equilibrium concentration of H2, but notice they gave us moles here. So we can do an ice table right away, but we need to get concentrations and not moles. So here we need to convert these to concentrations because you can't use moles in an equilibrium table or ice table, which is what we're going to use. So it's pretty simple. That's why they gave us the 3.0 liters. So remember, molarity, concentration is molarity, and that's moles divided by liters. So all we need to do is take the moles divided by the liters, and we've got our answer. So let's go ahead and do that. So here, we're going to take 0.75 moles, 0.75 moles, and we're going to divide that by the volume. And we said the volume was 3.0 liters. And when we divide that, we get 0.25 molar N2. And then we can do the same thing with our hydrogen, which is 1.20 molar. So we'll take 1.20 moles divided by 3.0 liters again. And here we're going to get 0.40 molar for H2. Okay, now that we have the initial concentrations of N2 and H2, we can now create our ice table. And so let's go ahead and write this down, ice. And so for the initial, for nitrogen, it was 0.25 molar, so we're going to put 0.25. And then for the hydrogen, the initial concentration was 0.40. And then to start with, we don't have any ammonia, so there's zero amount of ammonia there. Now that we have our initial concentrations, they told us that the equilibrium concentration of H2 is 0.10 molar. So let's go ahead and put that in our table. So that's going to be 0.10. And whenever you have all of the initial concentrations of the species in your balanced equation, and you have at least one equilibrium concentration of one of your species or products or reactants, you can fill in the rest of the table. You can figure out the change by noticing the difference between these two, right? So I started with 0.40, I ended with 0.1. That's a change of minus 0.3. So I lost 0.30 amount of my hydrogen to get to equilibrium. Now, notice here, this is a 1-to-3 ratio here, so the change is also going to be a 1-to-3 ratio. So if I lost 0.3 here, then I'm going to lose 1/3 of that because of the 3-to-1 ratio. So what is 1/3 of 0.30? Well, just take negative 0.30 divided by 3, and you'll get your 1/3, and that's going to be 0.1. So we're going to lose a 0.10 amount here. And then over here, notice this is a 1-to-2 ratio. So if I lost a 0.1 amount here, then I'm going to add a double of that amount here. So remember, we're going in this direction, so we're going to add here, and we're going to subtract here. We're going to lose reactants, and we're going to gain products. But the ratio is still the same. It's 1-to-2. If I lose an amount here by negative 0.1, if I'm losing 0.1 here, then I'm going to gain double that amount over here, which is 0.2. So I'm going to gain a 0.20 amount here. And now all I have to do is add these together. So 0.25 minus 0.1 gives me 0.15 at equilibrium here. And then adding these together, I get 0.20 amount here. So now we have the equilibrium concentrations for all of the species. So for N2, so the concentration of N2 at equilibrium is going to be 0.15 molar. We said that the H2 concentration was already given to us at equilibrium, and then this is the ammonia concentration at equilibrium. So the ammonia NH3 concentration at equilibrium is going to be equal to 0.20 molar. And that, ladies and gentlemen, is how you do part A. Now let's move on to part B. So for part B, they tell us if 0.30 moles of ammonia is removed through condensation and no other gases are added, right? No other gases are added. What are the new equilibrium concentrations of the three, nitrogen, hydrogen, and NH3, when it reestablishes? So what we have here, now we have to take this. These are now going to be our, we're going to establish new initial concentrations. We're going to disrupt this. So remember, Le Chatelier's principle, we'll talk about that in a moment. So let's go ahead and get started on this. Now, they're saying we're going to remove 0.3 molar. So the first thing we need to do is take the molarity of our ammonia, right? So remember, it's molarity. We're going to subtract out moles. So we need to know how many moles we have here. And so we're going to take the volume here, and we're going to multiply it by the concentration. So let's go ahead and do that. So we've got the concentration of ammonia. We got our 3 liters, so 3.0 liters over 1. You can use molarity as a conversion factor because it's moles over liters, so you can use it to convert from one unit to another. So here we're starting with liters. We can convert it to moles using molarity as a conversion factor. So the molarity is 0.20 moles of NH3 over 1 liter of solution. So liters cancels out. So 3.0 times 0.2, that's going to be 0.60 moles of NH3. So at equilibrium, this is the number of moles we have in solution. So, but they tell us we're going to lose 0.30 moles of that. We have 0.60 moles, so let's subtract the 0.3 from the 0.6, so let's do that here. So we're going to lose 0.30 moles of that, and so we get 0.30 moles of ammonia left. Okay, so we've removed 0.3 moles of ammonia. So now we're not at equilibrium anymore. So remember, we were at equilibrium. We didn't change anything, but now we're changing something. And so now we have disrupted equilibrium. So now we have to reestablish equilibrium. So now what we have right now is going to be our initial concentration. So now we have to do an ice table again. So let's go ahead and do that. So we're going to erase this. So we didn't change the N2, so that's going to start at a concentration of 0.15 molar. And we didn't change anything about the hydrogen, so that's going to start at the same concentration that we had at equilibrium. But remember, these two are no longer at equilibrium, so they're now going to be the initial concentrations. And again, the reason they're not at equilibrium anymore is because we changed the amount of NH3 here. So now we have this number of moles, but again, before you put this into the table, we have to change the moles of NH3 back to molarity. So let's go ahead and do that. So we have 0.3 moles, so 0.30 moles of NH3. And again, we're going to divide it by the volume, which is 3.0 liters. And of course, that's going to give us 0.10 molar to start with. So our initial concentration of ammonia this time is 0.10. And so that's what we're going to start with for part B. Okay, so the next thing we need to do is figure out which direction is this going to proceed. So there's a couple ways we can do this. One way is to use your reaction quotient and compare that to K. So we need to calculate K. We're going to need to calculate K based on our previous information before we messed up the equilibrium. So we have to go back to what our original equilibrium concentrations were. And if you remember, those were 0.15, 0.1, 0.2, right? So let me write that down here. So 0.15, 0.1, and we had 0.20 for that. And remember, K, so the K of this reaction, the equilibrium constant expression, is going to be equal to K, and it's the products over reactants, concentration of products over concentration of reactants raised to their the powers of their coefficients. So here we got the concentration of NH3, and that's going to be squared because we have a coefficient of 2, and then that's going to be divided by the concentrations of the reactants. So we have the concentration of N2, and its coefficient is 1, so we have a 1 power here. We don't write the ones. And then we got the concentration of NH3, and again, because that has a 3 there, then we're going to have a cube there. And so to find what the equilibrium constant is, we just plug in the values here. So for NH3, it's 0.2, and that's going to be squared, divided by the concentration of N2, which is 0.15, 0.15. And again, divided by 0.10, 0.10, and that's going to be cubed. And so you do your calculation using a calculator, and when you do that, you get 266.67. 266.67 is the K value. Now that we have our K value, we can take the initial concentrations and solve for the reaction quotient Q, which is the exact same formula except we're using initial concentrations instead of equilibrium concentrations. So if we calculate that here, Q is going to be equal to the same equation. So we got Q is equal to NH3 squared over the concentration of N2 and the concentration of NH3. Oops, not NH3, sorry. That's going to be H2. Oh, did I write any? Sorry, this should be H2. My bad. Sorry about that. That should be, keep writing the wrong thing. H2, there you go. H2, my bad. And then so this is H2 as well. And that's cubed. So now we're going to plug in the values here. So that's going to be equal to, so NH3 squared, that's 0.10 squared, 0.1 squared. And that's going to be divided by N2, which is again 0.15. And then we're going to divide by 0.1, 0.10, and that's cubed. And again, if you calculate this out, you get 66.67. And so here you can see that Q is less than K, which means, remember, it's a ratio of products over reactants. So if your Q is smaller, that means that the ratio is smaller here, which means that this denominator, or the numerator here, is smaller, and then the denominator here is larger. So a smaller numerator and a larger denominator gives you a smaller ratio, which is what K is. Again, remember the ratios here are the same. Q just is smaller. That's going to indicate that compared to what you should have at equilibrium, Q is too small, meaning that you don't have enough product and you have too much reactant. So it's going to shift in the direction to make more product and use up more reactant. So it should shift in this direction according to Q being smaller than K. So it's going to shift to make product and use up reactant. Okay, that's the first way you could have done it. The second way you could have done it is you could just use Le Chatelier's principle. Apply Le Chatelier's principle. And Le Chatelier's principle says that whatever stress you do to the system is going to undo that stress in order to reach equilibrium, right? So if you disrupt equilibrium in a certain way, it's going to react or shift in a certain way to undo what you did, right? So what did we do? We took away some of the NH3, the ammonia. We removed some ammonia. So the reaction is going to shift in the direction to make more ammonia, to put some of that ammonia back that we removed. So in order to do that, it's going to shift towards making more ammonia. So it's going to shift in that direction. So either way, you could have figured it out, either using Le Chatelier's principle or using K versus Q and comparing the value of Q to K and determining which way it's going. So now that we know which way it's going to shift, we can go ahead and do our ice table again. Okay, so here I'm going to write what the K value is. So here K is 266.67. Okay, now let's go ahead and fill in the rest of our ice table. So we're going to lose an X amount here because it's going this way. Again, because of the stoichiometry, that means we're going to lose an 3X amount here. And then we're going to gain here a 2X amount here, again, because of the stoichiometry 2, 3, 1. And then now we add these together. So we're going to have 0.15 minus X. We're going to have 0.10 minus 3X. And we're going to have 0.10 plus 2X. Okay. Now that we have our equilibrium concentrations in terms of X, we can now plug it into the K expression that we had before. Just a reminder, again, K is equal to the concentration of NH3 squared over the concentration of N2 and the concentration of H2 cubed, right? So we don't need this anymore, so let's go ahead and erase this to give us some space. Okay, so now, since K is equal to 266.67, we can now plug in these expressions into the equation here. So this is going to be equal to NH3 squared. This is the NH3 part, so it's going to be 0.1 plus 2x squared, and that's all going to be over, this was the N2, right, N2, so 0.15 minus x, and then we're going to divide by this here, 0.10 minus 3x, and remember this is cubed, right, that's cubed. And so let's go ahead and erase this. And so you could see right away that this is going to be quite a beast of a problem to solve. You're going to end up with a x to the fourth in some place. So we're going to have a polynomial equation. Notice that we can't do the x is small approximation because if you see the k value is rather large, which means it favors products, and so it's going to shift a lot towards that direction. Also, if we were to eliminate all the x's, we wouldn't have any x's left because we're adding 2x, we're subtracting an x, we're subtracting 3x. If we applied the x is small approximation, all of these would disappear, and so that would not help us at all. So we have to solve the equation. So let's go ahead and do this a little bit. Let me show you. So we got to unfoil this, of course. So it's going to be 266.67 equals, and then when you undo this, you get, what I get, 0.01 plus 0.4x plus, what else did I get? 4x squared. All over, and then we have 0.15 minus x, and then you have 0.10 minus 3x cubed. So, and then what you can do here is you can multiply these out, you can multiply this out, cube it, multiply that, and then divide, or you would multiply both sides with the bottom to get it over here, and multiply through there. Let's see what we got here. Okay, so when you go ahead and do this, right, so then this is going to be equal to 0.01 plus 0.4x plus 4x squared. And then when you undo all of that, you get 0.00015 0.0015 minus 0.0145. Is that right? 145 x plus 0.225x squared, 0.225x squared. I told you this is going to be ugly. Minus 4.95 minus 4.95x cubed, and then plus 27x to the 4. 27x to the 4. So now we have this whole thing. So this whole thing, and this is equal to 266.67. And then what you can do is take this bottom part and then multiply it both sides and multiply it on this side over here. So then what you got is, if I do that, I get, let's see, what do I get? 0.04. So I'm going to have 0.04 minus 3866 minus 3866, 3.8, sorry, that's 3.866 x minus 60 x squared. Let me double check that. No, that's plus 60x squared. And then I have minus 1320 x to the third plus 7200.03, and that's x to the fourth. Oh, I'm sorry, that's 0.09. Sorry, x to the fourth. And then that's going to be equal to this part on top. So that's going to be equal to 0.01 plus 0.4x plus 4x squared. So now you have this equation here. And then the last thing you need to do is subtract this and put it over here, so we have this equal to 0. Oops, I have this off the screen. Sorry, so that should be plus 4x squared. Okay. So now it's minus 0.01 on this side, minus 0.01 on that side. We're going to subtract 0.4x on this side. And we're going to minus 0.40x on that side. And then we're going to subtract 4x squared over here. And we'll subtract 4x squared over there. And then what you finally get for an equation, let me erase this, is 0.03, so we get 0.03 minus 4.266 minus 4.266x plus 56x squared, and then the rest are the same, minus 1320x cubed. I'm going to erase this, get this out of the way. And then we have plus 7200.09 x to the fourth equal to 0. Okay, so now that you got this equation, you just have to solve it. Now, at this point, you could plug it into an online polynomial calculator and figure out what x is. That's pretty much what I did. Now, these numbers might be slightly off because I may have rounded a little bit here and there. So just be aware of that. Your numbers might be slightly different than mine, but they're pretty much the same. So here, what I got when I plugged that into the online calculator, I got x is equal to 0.0076, oops. So it's 0.00767, or x is equal to 0.15674. 0.15674. Let me 15674. Yep. So I got these two numbers given to me. Now to figure out which one is the correct one, we go back to the original concentrations, right? So if you remember, the concentration of N2, so the concentration of N2 was equal to 0.15 minus x, 0.15 minus x, and the concentration of H2 was equal to 0.1 minus 3x, and then the concentration of NH3 was equal to 0.1 plus 2x, 0.1 plus 2x. Now, if this is the x value, 0.156, if you subtract it from here, you're going to get a negative value for your concentration of N2. And then even here, if you put it in for x, you're going to get 3 times that amount subtracted from 0.1. You're definitely going to get a negative value for this. So this value leads us to absurdity, where you can't get a negative concentration. So that can't be it. So this is our x value. So all we have to do now is subtract that from each of these. So this is going to be 0.15 minus 0.00767, and that gives us 0.142 molar, 0.142 molar, and then the same thing here. So we're going to have 0.1 minus 3 times x, which is 0.00767, and that's going to give us, what did that give us? That gives us 0.0769, 0.0769 molar, and then this is going to be equal to 0.1 plus 2x, which is 0.00767 again. And so when we add that together, we get 0.115. 0.115. And that, ladies and gentlemen, is how you solve part B. And again, these numbers might be slightly off than what your numbers. If you didn't round as much as I did, I might have rounded a little bit more. You might round a little bit less, but you should get something close to these answers, or very close to these answers. If you round this to 2 sig figs, this is going to be 0.14 molar. If you round this to 2 sig figs, it's going to be equal to 0.077 molar. And if you round this, it'll be 0.12 molar. And so that is how you got these. This is how you get the problem. This is how you get it right, ladies and gentlemen. So I hope this was helpful. If you enjoyed this video, if this helped you in any way, then please by all means like the video, share the video, hit that like button down there. Also, make sure you subscribe to my channel. Help me out. When you do that, click the notification bell up there and click all so you can be notified by all the videos I put out. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. Thanks for joining me and have a great day.